Beneath the most heavily monitored patch of fault line on the planet, something has been moving for over a decade, and until a few weeks ago, nobody noticed. The San Andreas Fault at Parkfield, California, ground zero for the 1857 magnitude 7.9 rupture, gave up a signal that never should have stayed hidden. Buried inside 8 years of archived strain meter data, artificial intelligence found 92 silent slips in the rock, motion with no shaking, no warning, no seismic wave at all. Scientists know it happened. They still cannot fully explain what it means for the next big one. Parkfield is barely a town. Fewer than 20 people live there, in a dry fold of Central California ranch country, where cattle outnumber cars and the local sign proudly calls it the earthquake capital of the world. That is not exaggeration. This exact stretch of the San Andreas has been wired with more seismic instruments per square mile than almost anywhere else on the planet, because it is famous for rupturing on a pattern scientists thought they understood. In 1857, this section let go in a magnitude 7.9 earthquake that tore across more than 200 miles of California. A quake that size, at that shallow depth, does not just shake the ground near the fault. It can be felt hundreds of miles away, and it can shift the earth by as much as 30 feet in a matter of seconds. The 1857 rupture, known today as the Fort Tejon earthquake, cracked adobe walls and toppled chimneys across a sparsely settled California, and shook the ground hard enough to be noticed as far away as Las Vegas. That event is the reason this fault segment gets studied so intensely in the first place. Parkfield sits almost directly on that historic rupture line, which is exactly why the U.S. Geological Survey and university researchers have kept instruments buried in the rock here for decades. If anywhere on Earth should have nothing left to hide, it is this 15-mile stretch of fault. That is what makes the new finding so unsettling. A team led by geophysicist Zara Zali, working with colleagues at the GFZ Helmholtz Center for Geosciences in Germany and the EarthScope Research Consortium in the United States, went back through 8 years of data collected from 4 borehole strain meters near Parkfield, instruments sensitive enough to detect rock stretching by a fraction of a millimeter. That data had been sitting in archives since 2016. Nobody had flagged anything unusual in it. Then, the team ran it through a machine learning model trained to spot patterns too subtle and too buried in noise for a human analyst to catch by eye. The AI found 92 events the original researchers had missed. Slow, silent slips in the fault, each one lasting anywhere from a few minutes to several months, releasing stress with no earthquake, no rupture, and no shaking a person could ever feel. The study was published this summer in the journal Nature Communications, and it forced an uncomfortable question. If this exact patch of fault, the most watched patch of fault on the planet, could hide 92 separate slow-motion events for over a decade, what else might it be hiding right now? Picture what a borehole strain meter actually is. It is a sealed instrument lowered hundreds of feet down a narrow drilled hole, sensitive enough to register the surrounding rock stretching by less than the width of a human hair. There is no dramatic shaking to point a camera at. No cracked road, no rattled window, no dust shaken loose from a barn roof. The only trace any of this ever left behind is a slow drift in a line on a graph, recorded continuously for years by machines nobody was actively watching. That is the entire crime scene. 8 years of quiet lines and a pattern that took a machine, not a person, to finally notice. The easiest explanation is also the most boring one, and boring is usually where a good investigation starts. Parkfield is already famous for something called fault creep, a slow, continuous slide where the two sides of the fault inch past each other at about the pace your fingernails grow without ever building toward a big earthquake. Scientists have documented that creep for decades, so the first assumption is simple. These 92 events are probably just that same, well-understood creep, finally showing up more clearly in 8 years of newly reanalyzed data. That assumption is not unreasonable. Parkfield's steady creep is real. It has been measured for years, and it helps explain why this segment does not build up stress the same way some locked sections of the San Andreas do. But steady creep is, by definition, steady. It does not turn on and off. What the AI found was not a smooth, continuous slide. It was 92 distinct separate bursts, starting and stopping, some lasting minutes, some stretching across months, layered on top of the fault's ordinary creep like a second signal hiding inside the first one. That is the detail that breaks the simple story. The most monitored fault segment on Earth was not just creeping quietly the way everyone assumed. It was pulsing in a pattern nobody had ever cataloged, using instruments that had been running the entire time. Before celebrating a discovery, any serious research team tests the boring explanations first. The first candidate was not geology at all. It was the instruments. Borehole strain meters are exquisitely sensitive, which means they are also sensitive to things that have nothing to do with the fault. Temperature swings, shifting groundwater, even changes in atmospheric pressure. If the AI was just picking up weather noise dressed up as tectonic drama, the whole finding would collapse. That is not a small risk to rule out. A strain meter buried near the surface can drift after a heavy rain or twitch when a nearby well is pumped. So the signals researchers kept had to survive a filtering process, checked against seasonal patterns, against known equipment quirks, against anything that could explain the same wiggle without a single inch of rock actually moving. 92 events made it through that filter. That does not prove every one of them is geological. It does mean the easy dismissal that this was all just weather and machinery does not hold up on its own. Here is where the story holds. Separately from the strain meter data, scientists have spent years building an independent catalog of roughly 500,000 low-frequency earthquakes, tiny quakes too small and too deep to ever be felt, but real enough to be measured on seismometers. When researchers laid the 92 AI-detected slow slips over that catalog, a pattern emerged. Again and again, the slow slips lined up in time and space with clusters of those tiny quakes, within about 6 miles and never deeper than roughly 12. Random instrument noise does not organize itself around an independent catalog built from entirely different instruments. That overlap was the first real evidence that something physical was happening underground. So if it is not noise, and it is not ordinary creep, what is it? This is where the story gets genuinely strange, because until fairly recently, mainstream seismology did not think this kind of slow, silent slip could happen on a fault like the San Andreas at all. Slow slip was first documented in subduction zones, the enormous fault systems where one tectonic plate dives beneath another off the coast of Japan or the Pacific Northwest. For a strike-slip fault, where two plates grind sideways past each other the way the San Andreas does, the idea was considered close to impossible. One geoscientist has described the old thinking bluntly. Slow slip and low-frequency quakes were treated as essentially non-existent on faults like this one, not that long ago. Think about why that distinction matters physically, not just historically. In a subduction zone, one plate is diving beneath another at a shallow angle over a huge, gently sloped contact area, which gives stress room to release gradually. The San Andreas is nearly vertical, two plates grinding past each other edge to edge, a geometry that seismologists assumed was built for sudden, violent slip, not a slow, quiet release. Finding slow slip here means the fault has more than one way of moving that scientists did not fully account for, and every one of those extra pathways changes how you calculate where built-up stress actually goes. And the San Andreas is not some remote curiosity. The same fault system that runs through Parkfield's empty ranchland continues south into a corridor of more than 20 million people across greater Los Angeles and San Diego, and north toward the San Francisco Bay Area. Nobody is saying Parkfield's slow slip threatens those cities directly, but understanding how stress actually moves along any stretch of this fault matters far beyond one sparsely populated valley. Because the San Andreas does not behave as separate, unrelated segments. It behaves as one long, connected system. This is not even the first time Parkfield has upended that assumption. Back in the mid-2000s, Berkeley researchers monitoring this same stretch of fault discovered deep, rumbling tremors, a related but different phenomenon that had also been thought exclusive to subduction zones. They tracked more than 2,000 tremor episodes between 2001 and 2009 and found the frequency spiked after 2 moderate earthquakes struck nearby, in 2003 and 2004. At the time, a USGS scientist cautioned that it was still too early to know what that long-term pattern really meant. Nearly 2 decades later, that caution still holds, even though the picture is now far more detailed. Here is the mechanism the new study actually points to. A fault does not only release built-up stress through earthquakes. Sometimes it exhales that stress quietly, through a slow slip that never breaks the surface loudly enough to shake anything. According to Zali and her co-author Patricia Martinez-Garzon, these slow slips appear to help set the rhythm for the tiny low-frequency quakes nearby, essentially earthquakes in slow motion that are not isolated at all, but tied into a much larger ongoing transfer of stress moving through the rock. Every time one of those quiet exhales happens, it may nudge the timing of the small quakes around it. So why did the most watched fault segment on Earth miss this for over a decade? Because slow slip falls directly into a blind spot. It is too gradual and too quiet for a seismometer, which is built to catch sudden shaking. And it is usually too subtle for GPS stations, which are built to catch a location physically moving, not deep rock deforming in place. Borehole strain meters were the one instrument sensitive enough to catch it, but even they produce signals too faint and too buried in background noise for a human researcher scanning 8 years of squiggly lines to reliably pick out. It took a machine trained specifically to hunt for that pattern to finally see it. That should feel like a clean resolution. It is not. The independent catalog held close to 500,000 low-frequency quakes across those same years and instruments. The AI found only 92 matching slow slip events, 92 matched events, against nearly 500,000 small quakes total. The correlation is real, but it is far from universal. The study's own authors are careful with their language here. Slow slip may influence the timing of these small quakes. Not controls it, not causes it, may influence it. That is an honest scientific hedge, and it is also the point where the story stops being simple. To understand why that hedge matters so much, you have to go back to something else that happened at Parkfield, something that still stings a little in the seismology community. This exact segment of the San Andreas does not just creep and rupture in dramatic megaquakes like 1857. It also produces a much smaller, moderate earthquake, somewhere around magnitude 6, on a pattern that once looked almost predictable, roughly every couple of decades going back through the historical record. That apparent rhythm was convincing enough that in 1985, the U.S. Geological Survey launched one of the most famous experiments in earthquake science, the Parkfield Earthquake Prediction Experiment. Based on the pattern, they forecast a magnitude 6 earthquake would strike before 1993, and they built an entire monitoring array around that single forecast, creep meters, seismometers, magnetometers, and eventually a deep borehole observatory drilled directly into the fault zone. For a while, this quiet ranching valley became one of the most closely watched pieces of ground on the planet, with scientists and journalists waiting for a specific earthquake on what amounted to a schedule. It did not happen in 1993, it did not happen in 1994 or 1998 or 2001. The magnitude 6 earthquake scientists had confidently predicted on the best instrumented fault segment on the planet, using one of the most carefully reasoned forecasts in the field's history, finally arrived in 2004. 11 years late, on a fault segment surrounded by more sensors than almost anywhere on Earth. That failure is exactly why today's researchers are being so careful with their language. This new slow slip discovery is not a prediction tool, and nobody involved in the study is claiming it can tell you when, where, or how large the next earthquake will be. The 1980s experiment leaned on the timing of past earthquakes repeating on a schedule. This new research leans on a completely different kind of data, deep, quiet rock deformation, read by an algorithm instead of a calendar. They are both signals from the same patch of fault, but they answer different questions, and Parkfield has already taught this field, painfully, what happens when a confident forecast meets an uncooperative fault. The Parkfield story does not exist in isolation this year either. In May, a separate research team drilling off the Oregon coast found paired layers in seafloor sediment, evidence that shaking from a past Cascadia megaquake and a past San Andreas rupture landed close enough together in the geologic record to raise the question of whether one fault can help trigger the other across hundreds of miles of coastline. The idea is not that one always causes the other. It is that a large enough jolt on one system might be capable of nudging stress on the second, an open, still debated hypothesis rather than a settled mechanism. And in June, researchers from the University of Bern examined roughly 1,000 years of earthquake history around Cajon Pass, a narrow structural choke point on the southern San Andreas and San Jacinto fault systems, and concluded that stress there has built to some of the highest levels in that entire 1,000-year record. Researchers have started calling structural choke points like this one earthquake gates, places where geometry itself controls whether a rupture on one fault segment can jump onto the next. It would be easy and dramatic to chain all three of these stories together into one giant warning. Do not. They describe 3 different fault segments using 3 different methods published independently by 3 different research groups. There is no confirmed physical link tying the slow slip at Parkfield to the stress building at Cajon Pass, or to a hypothetical trigger from Cascadia. The real twist here is not a hidden connection, it is the opposite. The timing of these publications landing in the same year is very likely coincidence, not evidence of one unfolding crisis. What is left once you strip away the temptation to connect every headline is something narrower and still genuinely significant. A newly documented, still being mapped category of silent motion on a fault segment with a track record of violently rupturing and then defying attempts to predict it, and an honest, unresolved question about how much that silent motion actually matters for what comes next. So here's where the investigation actually stands. Confirmed, 8 years of strain data at Parkfield contain 92 previously undetected slow slip events, many of them lining up in time and location with clusters of small, deep earthquakes nobody felt. Confirmed. This kind of motion was considered close to impossible on this type of fault until recently. Interpreted cautiously, these silent slips may help set the rhythm of stress moving through the rock between larger earthquakes. Still unproven whether tracking them in real time could ever meaningfully warn anyone before a damaging quake. Researchers have said they want to expand this same AI approach beyond Parkfield to other fault segments and eventually to live, continuous data instead of an archived 8-year window. That means watching for whether new slow slip events keep lining up with clusters of small quakes in real time, whether the depth or location of that activity migrates along the fault, and whether similar silent bursts turn up on segments that have never been checked this closely before. The U.S. Geological Survey's position has not changed either. No earthquake has ever been successfully predicted, and this study does not claim to be the exception. It only claims that the fault has one more voice than anyone realized, and that voice is finally being heard. What has changed is quieter than that. Somewhere under that dry stretch of ranch country, past the cattle and the sign calling it the earthquake capital of the world, a borehole strain meter is still recording, second by second, the same kind of silent movement that stayed hidden for a decade. Nobody is watching for the ending of that story yet. They are just watching the needle.